Okay, so we are in chapter 7. We're sort of in the middle of chapter 7. The first two sections, we introduced the law of sines and started solving triangles. Basically, the idea of solving triangles was if we are given 3 bits of information about a triangle, then we try to find out all the rest. And the bits of information I'm talking about are like sides and angles. And so in 7.1, this was broken down into different cases. And so just to do a quick reminder, we use the law sines in 7.1 and 7.2. We use the law of sines when we had angle, side, angle for a triangle provided, or when we had side, angle, angle, or angle, angle, sides. When you have 2 angles and a side that's between them, or 2 angles and a side that's not between them, then we use the law of sines to solve those triangles. And I believe this was case 1. Then we also, tangentially to this, we also, if we were given side, angle, side, we didn't solve the triangle then, but we got the area formula. Like that was in 7.1. So then in 7.2, we looked at when you had 2 sides and an angle, which was case 2. And again, we used the law of sines, but then all of a sudden there were different possibilities that you might have no triangles that could have those 2 sides and that angle. You could have exactly 1, or that there were 2 possible triangles, both would have those 2 sides and that angle. And so we had to break down to those different possibilities. So it was a bit ambiguous, was the word they use, but we'll just say not sure which triangle. Not sure which triangle is needed. There could be more than one. There's more than one. More than one sometimes. Possibly. And so that's what we did in 7.2. So we're kind of we're putting this all together over several sections. And so what they're going to show us in this section is cases 3 and 4. Which will be for side, angle, side. We had side, angle, side before for the area of a triangle, but now we're going to solve the whole triangle with side, angle, side. And then finally SSS, which is where you know all 3 sides of the triangle. And so in order to look at these cases and solve triangles in these situations, we need the law of cosines. So it'll be similar to the law of sines in that it involves cosine and that it helps us solve for missing parts of a triangle. So just putting them here, the law of sines, which basically said that for any triangle, it doesn't have to be a right triangle, could be for any triangle, that the sine of angle A divided by side A, which is opposite that, is going to be the same fraction as the sine of B over side B, or the sine of C, angle C over side C. And that this is true. So this put us in a position where if we knew 3 of these 4 in any compared fractions, we could solve for the missing part. So we used that a bunch of times for case 1 and case 2 in 7.1 and 7.2. So what is the law of cosines going to say? Unfortunately, it'd be nice if it was the same as this and we just replaced cosines or something simple, but it's a little bit more like the Pythagorean theorem. So let's advance here a bit. So they remind us of a fact and a sort of side length restriction. In any triangle, the sum of the lengths of any 2 sides must be greater than the length of the remaining side. And again, if you just think about a basic triangle here, the idea is if I'm got A and B and C, these sides may all be different. Two of them may be the same, all three of them may be the same. But if you add any two of them, it's got to be longer than the third one. And if I examine, in this case, the shortest two, so A and B are the shorter two, well, basically, if I'm thinking about the length of side C, that's the distance from the left end of C to the right end of C. And if you go from one point to another in a straight line, you can't get there any quicker than that. That's going to be the shortest distance. The shortest distance between 2 points is always a straight line. So if you think of the length of a side as the distance between the 2 points at its ends, well, then the length of the other side is just a longer way to get from one end of C to the other end. So if I have point 1 and point 2 here, you can think of what this box is saying is that it'll always be the shortest distance to go from point 1 to point 2 along one side. That'll always be shorter than going from point 1 to point 2 by going along side A and then by going back along side B to get to point 2. Because you didn't go straight from 1 to 2, it's going to take longer. That means those sides have to add up to more than side C. And that's true no matter which ones you're talking about. And it's pretty commonsensical that it makes sense that it's going to take longer to go from one side to the other than by going around the other two sides than going directly across. But that's what this states. So having said that, like with the law of sines, they're going to give a derivation of how they came up with the law of sines, where they show some slides to show a proof of why the law of cosines works. But I'm just going to go straight to the law of cosines because we want to practice using it, and you're welcome to review these slides. And there's only a couple of them, and here's the law of cosines. So when looking at the law of cosines, we have three different things given. In any triangle with sides A, B, and C, then the square of any one of the sides is equal to this combination on the right of the other two and the angle opposite side A, or side B, or side C, correspondingly. So what does this mean in a triangle? So again, you have angles on the vertices, and you have sides opposite those angles. And so when we're talking about side A here, as they are in the first one, you can calculate side A using side B, side C. So you're using B and C, and you're using B again, and you're using C again, and you're also using angle A. So you can get side length A if you have the angle opposite A and the other two sides. And notice that if you have these three, what you have is side, angle, side. Side C, angle A is between side C and B and side B. And so what this allows you to do is if you're given side, angle, side, then you can find the third side from that. You have two of the sides, you have the angle between them, then you can get the side opposite that angle, which will be the side that you don't know. So what these allow you to do is, given side, angle, side of any triangle, you can get the third side. So that's what the law of cosines allows us to do. Now, my suggestion was that you think about this like the Pythagorean theorem. So let's take a look. Pythagorean theorem would say that if you have a right triangle, and we call the smaller or the legs A and B, then the larger side C, the hypotenuse, because it's opposite the 90-degree angle, we know that you have A squared plus B squared equals C squared. Or C squared equals A squared plus B squared, if I write that in terms of C. Well, notice how this compares to the c-squared version of the law of cosines. And so the idea here is that if angle C, which in this case would, in a right triangle, would be 90 degrees, if angle C is 90 degrees, well, then that whole term on the right there becomes a 0. So the Pythagorean theorem is basically the law of cosines, where the angle in between the two sides given happen to be a right angle. And then you're solving for the hypotenuse to get the third side. And so what happens is when you have a right angle, then you get the Pythagorean theorem. But when you don't, then you can still use the modified version where you adjust by subtracting off from a squared plus b squared, you subtract 2ab times cosine of whatever that angle is. And once you don't have a right triangle, then you don't have a hypotenuse and the two legs. All three are just sides. And then you can do that for any one of the sides in the triangle that's missing. So given any two sides and the angle between them, you can find the missing side by plugging into the law of cosines. And then, of course, since you're getting the square of the side you want, you would square root to get the answer of what you want. And now we'll just put this into action in some examples. All right, so try to envision using the law of cosines to solve for a missing side. You would just take the expression on the right of the one you want to solve for. If you want to solve for a squared, you're going to plug in b, c, and angle A into this expression here. And you're going to get a number. You're going to punch all that on your calculator. You're going to get an answer. And then when you get that number to figure out what A is, you're going to take a square root, because what you got was the value of a squared. And then when you square root that, you'll get the value of A. So that's the idea here. That's how the law of cosines allows us to solve for unknown information about a triangle and eventually for the whole thing. So they give a note that basically says what I just said. If C angle is 90 degrees in the third form of the law of cosines, then cosine of C would be 0, since cosine of 90 is 0, and the formula becomes the Pythagorean theorem. So let's look at this example 1. It's got a nice little picture. Applying the law of cosines in a side angle side situation. The surveyor wishes to find the distance between two inaccessible points, A and B, on opposite sides of a lake while standing at point C. She finds that B is 259 meters, so we know psi B. A is 423 meters, and the angle ACB measures 132 degrees 40 minutes. Find the distance C. So you're basically trying to find the distance straight across the lake when you're not able to walk that length, because you'd be walking across the lake. But you can find it by walking around the edges of the lake and setting up this triangle and solving for the missing side that goes across the lake. All right, so how would we do this? Well, we would just I'm sure they're going to demonstrate it for us, but we want to find C, and we know that C squared is equal to A squared plus B squared, just kind of starting with the Pythagorean theorem. But then because we don't have a right triangle, you say, I'm just going to subtract 2AB cosine C. And that's the way I suggest you think about the law of cosines, is that it's just a modification of the Pythagorean theorem, where you solve for one side in terms of the two others. So in this case, we're given an A value of 423. So I would say 423 squared, and a B value was 259 squared. And I would subtract 2 times 423 times 259 times the cosine of the angle, which was 132 degrees and 40 minutes. And again, if you don't have like a way to put minutes on your calculator, because you're just going to type all this on your calculator, then to put this into decimal form, this would be 320 degrees plus 40 over 60, because a minute is a 60th of a degree and you have 40 of them. So that's 40 60ths of a degree. And you can see that reduces to 2/3. So this would be 320.6 with a bar on it degrees, repeating 6. Anyway, you can convert the minutes into degrees. We haven't done that for a few chapters, so just as a reminder, so that you can punch all this on your calculator. Then I would just type all that in and square root to find out what C is. So C is going to be equal to the square root of the results of all that stuff. Questions, comments, discussions about that?
Yeah, I have a question.
Yeah.
You put in cosine 320 degrees, but isn't cosine 130?
Yep, thank you. 320 is pretty silly. Keep me honest. Yeah, I don't know where I pulled that out of. 132. 32. Oh, the 320 had the 32 part right. I don't know what I was doing. Good question. Other questions? Anything here I should explain better or elaborate on? Did I think that was 320? My little brain, like, just look at that. Put the little degree like it's a 0. I have no idea. Okay, so I think they'll probably do this for us. So let's just see how they write this up. But I think it's kind of nice to just see how you can just grab the theorem. So yeah, they grab that, except they punch it in their calculator. So we'll see what their results were. Using the law of cosines, we know the lengths of two sides and of the triangle and the measure of the angle that's in between those. And they just plug those in as we just did. And they did do 132 instead of 320. Good for them. And then they got the result, which would be C squared. So then again, you would square root your answer from that stuff up above. And then they got 628. And again, these were measured in meters. So this would be 628 meters to use the correct units as well. All right, so it looks like pretty straightforward. And that's one of the nice things about the law of sines. Like the law, I'm the law of cosines compared to the law of sines. With the law of sines, you set up these two fractions and you often still have to sort of solve for something. And these, you're going to need to square root at the end, but it's kind of already solved for whichever side that you're trying to determine. All right, so here's example 2. So in this case, instead of making a nice picture with a lake or something, they're just saying, solve this triangle. And what they tell us is angle A and sides B and C. And so we can see we have side, angle, side, where the angle is between the two sides that we're told. And that in the side angle side, say, okay, when you see that relationship, you say law of cosines, and then you can solve the triangle by starting to solve for the side you don't know. So you solve for that side that you don't know using the law of cosines. So that's angle A, side A. And so they chose the A squared version of the law of cosines because they're solving the unknown side that's opposite angle A. And then they plug in sides B, C, and angle A. And then after they get that result, they took a square root to get 10.47 meters. Now, they do make a note here. It says B is less than C. They're talking about the angles. Angle B is less than angle C. Well, we don't know what those angles are, so how would we know that? Well, that comes from the fact that side C is bigger than side B. So angle B is less than side C since it's opposite the shorter of the two sides. Therefore, B cannot be obtuse. They're doing this because they're trying to give you the best pattern to solve the equation a little bit more quickly and comfortably. It's easier if you solve for the shorter angle first, because there can only be one right answer to that. So that they're pointing that out, and then they're saying use the law of sines to find the measure of another angle. But notice they chose B. Chose B to solve next. So they're not sort of stating it explicitly, but the reason they chose B to solve next here is because it cannot be obtuse. It's the smaller of the two sides here. And so for that reason, they're saying the process goes more smoothly if you choose to solve for that next. So then, now that we have now that they want this to solve for B, we have side B that's opposite that. And we now have angle A and side A. So because we have these three, we can now switch to the law of sines. And the law of sines will just be a little bit less involved. So if we know sides A and B, and we have angle A, we use those to solve for side B. Now that we know side A. And so they plug those in, and we don't know side B. And when they solve for side B, they get 56 degrees. So you plug in the three that we know, and then solve for the one that we don't know. We know this, we know this, we know this, and then we solve B, angle B. So then it says, now that we've found this last angle, there's this next to the last angle, the only angle that's left that we don't know in the triangle is C. And so we find the measure of the third angle by subtracting the other two that we figured out. So we know this is 56 degrees. We were given that this is 42.3 degrees. So if we subtract those from 180, we get that angle C is 81.7 degrees. And then you've solved the whole triangle. You found all the other missing parts. So they have a caution here, which is why they did it the way they did, that I tried to explain. Had we used the law of sines to find C, angle C, rather than B in example 2, they did eventually find it. But if they had started in the line, if they had chosen C here instead of B, then there might have been two possible solutions. It could have been 81.7 or its supplement 98.3, because the larger angle had those two possibilities. So if you find the smaller angle first that you know can't be more than 90 degrees, then there'll only be one answer. And then once you know that, you can use that and the other one you know to find the third one, and then you avoid this confusion that they're cautioning about here. So this is why they chose B. So to avoid, solve for the smaller angle first. So use to solve side angle side. Let's just review the process. To solve side angle side, you'll be given two sides and an angle between them. You first solve for the third side using the law of cosines. Then you'll have all three sides and you'll just not know two angles. You can see which of those two angles is the smaller of the two by looking at the sides opposite them. So solve for the angle that's opposite the shorter side of the two that were given. And then when you do that, you know your answer has to be less than 90 degrees. And therefore, when you solve, you'll get the single possible right answer, and you solve for that angle using the law of sines. Then when you've solved for that second angle, then you can get the third one by subtracting the other two from 180. And that avoids this issue here if you had solved for the bigger one first. So that's the overview of the process of how to solve any side angle side given triangle. So the nice thing here is that each of these solving processes is pretty straightforward. It's like a little checklist of things to do. Case 1, case 2, case 3, case 4, that will be true. But there's several different cases. You have to look at what am I given about the triangle that I'm solving, and then which approach do I use to solve it? Do I start with the law of sines? Do I start with the law of cosines? So that's why we have these letters to help us identify what we were given, and that's why we break it into these 4 different cases. All right, so the last one we want to look at is the situation of side, side, side. So now we're just given all 3 sides. So clearly we can't use the law of sines because any of the fractions we would make with the law of sines will have an unknown angle because we don't know any of the angles. And if that's the case, then no way could I have 2 of those fractions be set up where I know 2 of the 3. I'm unable to use the law of sines because I won't be able to get 3 out of the 4. When I set up 2 fractions, I'll only know 2 of the 4 things, and I won't be able to solve. So this is sort of the idea of why we have to use the law of cosines in this situation as well. So when we have all 3 sides, well, the law of cosines has been set up to solve for a side, a squared or b squared or c squared. So if we're not solving for a side, how do we do this? Well, as we see in the example here, they gave us 3 sides, a, b, and c. And they just took the law of cosines written out in terms of the side c. And what you'll see is normally we're given, if we're given side angle side, we'd know a, we would know b, and then we would know angle c between them. But if we don't know angle c between them, and I take that off, but instead I now know side c, well, then the only thing we don't know is angle c, and you can solve for that. So if we know all 3 sides, then the law of cosines, when you plug in all 3 sides, leaves you with cosine of an angle being equal to a number, and then you can solve that by using the inverse cosine. So they basically were solving it first for cosine by isolating the cosine c term here. So they're saying solve for cosine c. You could do that before or after you plug in the numbers, but it is kind of nice to see the formula before you plug in the numbers to get all of the arithmetic on one side. So they subtracted a squared from both sides. They subtracted b squared from both sides. Or actually they didn't. They moved this over to the left and they moved this over to the right. So they subtracted c squared from both sides and they added 2ab to both sides. And then they divided the 2ab cosine, and then they divided by 2ab to solve for cosine. Anyway, I'm babbling on. So they isolate cosine c, and they get this formula for the cosine of an angle determined completely based on the 3 sides of the triangle. So if you're given the 3 sides of the triangle, you can get the value of the cosine. And so they plugged all those in, and they got the value of the cosine. And then, of course, to figure out sine, you take inverse cosine of both sides. And they got 109.9 degrees. So remember, the cosine, inverse cosine function is always going to give you an angle between 0 and 180 degrees. And so that's good. Whatever the angle is, even if it's more than 90 degrees or less than 90 degrees, you're not going to get inverse cosine giving you a negative angle. Like inverse sine might give you a negative angle in quadrant 4 or something. But cosine, inverse cosine will always give you an angle in quadrants 1 or 2, always between 0 and 180 degrees. All right, well, once we know one of the angles and we have all 3 sides, then we can switch over to the law of sines. So if we just got angle C, then we would use that angle we just got, angle C, with side C. And then we also know sides B and A. So then we would get one of those. And so in this case, they said, all right, then we'll match that up with side B. So we know angle C, we know side C, we know side B, and then we can solve for angle B. We're getting angle B here. So they plugged in the angle that we just figured out and the sides that we know, and then they solved for sine B. And then again, once you have sine B is equal to some number, which you type in on your calculator, you take the inverse sine of both sides. And if that happens here, you should, it is possible if angle B was more than 90 degrees, then the inverse sine might give you a negative angle here, and you would have to use the properties of sine to get the positive angle by moving over to the other side of the sine function, basically. And so just keep that in mind, but I think this will work. This will pretty much regularly work. So this gives us angle B. And then of course, once you know angle C and angle B, you can subtract them from 180 to get angle A, whatever that third angle is that you don't know. Okay, so in this way, we've solved for the triangle. So let's pause here for a second. That's how they just finished. This was the completion of their example 3. And so just as an overview, if you are given side, 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 this is case 4, I believe, then we use the law of cosines to solve for the angle, to one of the angles, by plugging in all 3 sides and solving for the missing angle. Once we know one of the 3 angles, we can use that angle and its opposite side and one of the other sides in the law of sines to solve for another angle. And then, of course, once we know those 2 angles, we can subtract from 180 to get the third angle. And that is the process for solving a side, side, side triangle given. So let's look at their next example of doing the same thing. And this is designing a roof truss. So in a roof, you have a setup here, and we know the length of the 3 sides that are going to be put together to make the triangle: 9 feet, 11 feet, and 6 feet. And it says to find angle B. So they just want angle B in this case. They're not asking us to solve for the whole triangle. So if you are asked to solve specifically for angle B, then you would want to choose the law of cosines result for B squared, because that's the one that has angle B in it. And then, like we did in the earlier example, we would then solve for cosine of that angle in terms of the other 3. And it has the exact same pattern of answer. You plug in the numbers you were given, 11, 9, and 6. Then you take the inverse cosine of that, and that leads you in this case to getting approximately to the nearest degree, 33 degrees. So when you see that very focused just to solve for one of the angles, it goes pretty quickly here. Okay. So we have a nice summary here. 4 possible cases can occur when solving an oblique triangle. Again, oblique means not necessarily 90 degrees. As we saw when we're doing these solving processes, you could end up with a 90-degree triangle. But in general, if it's not known and it not having a not 90-degree triangle means oblique. So case 1, you are given side angle angle or angle side angle, meaning 2 angles and a side that's between them or a side that's not between them. And in both of those cases, you would use the law of sines after finding the missing angle. So it sort of gives you suggested procedure, which is nice to summarize the work that we did in the earlier sections as well. Step 1, find the third angle. Step 2, find the remaining sides using the law of sines. And that works for both of those situations in case 1, where you have 2 angles and a side. Case 2, you have 2 sides and an angle. And specifically, the angle is opposite one of those 2 sides. It's not between them, it's opposite one of those 2 sides. So that was the more ambiguous case that we looked at in 7.2. We still use the law of sines, but there were the different possibilities of whether you have 0, 1, or 2 triangles. So it says this is ambiguous. There may be no triangles, 1 triangle, or 2 triangles. So find an angle using the law of sines it may be that when you try to solve, the angle can't exist because the sign is supposed to be equal to a negative number. That would be an example where the case is that there is no there's no triangle that works with the information with the side angle given. Find the remaining angle using the angle sum formula. So if you can find an angle using the law of sines, then you find the remaining angle. And there was a possibility that you might have two different angles that would work. And that's why you might have two triangles. So that's why there's also some ambiguity there. You may recall from our previous section. And then once you've done that, find the remaining side using the law of sines again. Find the remaining side using the law of sines again. And it says if two triangles exist, repeat step 2 and 3. So if you get two possible angles, then you might have to say, well, in each of these cases, what would the remaining side be? So that was that's specifically for side angle. So that's the one where you know there might be some more steps and there might be some ambiguity. So then in case 3, as we just discussed, if you have the angle between the two sides given instead of opposite one of the two sides given, well, then it's more straightforward, but we can't use the law of sines to start anymore. Instead, we have to use this new law, the law of cosines. So if you have two sides and an angle between them, find the third side using the law of cosines. And then once you know that third side, then you will have the parts you need in the law of sines to find the other angles. So then find the smaller of the two angles using the law of sines. Now notice it says find the smaller of the two remaining angles, and that you can judge by looking at the sides opposite them. And so if you find the smaller of the two remaining angles, then you'll be able to find the remaining angle using the angle sum formula, and that will always be correct. Whereas there's a little confusion if you don't find this, there's a possibility of confusion if you don't find the smaller of the two angles first. There might be two possible answers and you'd have to eliminate one. So that's a much more straightforward process. We don't have ambiguity, you just go through the steps. And then lastly, and also somewhat nicely, there's no ambiguity when you have all three sides. You definitely can't have two triangles with all three sides given. There's only one triangle that can be formed with those three lengths that are given. And first you would find the largest angle using the law of cosines. So the way to find the largest angle is to look for the angle opposite the largest side. And again, this is to avoid the ambiguity of there being more than one possible or something like that. Find either remaining angle, then you can switch to the law of sines to find another angle, and then you can find the last angle by subtracting the two you found from the 180 total. So this is a nice overview with the suggested procedure for each of the 4 cases. And so when you are given a problem, now that we've done all of these, you might be given any one of these sets of 3 information bits about the triangle. You may be given all 3 sides. You may be given 2 sides and an angle that's not between them for case 2. And so based on which you're given, you then use the appropriate procedure and strategy to solve the triangle. And so this is a nice summary here. What's up here? All right, so we have one more thing to look at, and that's good because we've only got about 9 minutes left, so that's good timing. Now, if you have side, 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 we have another formula for the area of a triangle. Now, you may recall we had the area given before when we had side, angle, side. And you could, of course, with side, 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 find out the missing angle. But again, if you just want to use 3 sides and you don't want to have to come up with the angles, this formula does that as well. So let's look at how this formula allows you to get the area of a triangle just using the 3 side lengths. So first they have you calculate this thing in the formula called S, which is the semi-perimeter, which just means half the perimeter. Like you've heard maybe of semicircle, it's half a circle. So semi-perimeter is half the perimeter. The perimeter is where you add up all the sides. And so this is the perimeter, A plus B plus C. And then to get the semi-perimeter, you just divide that by 2 or multiply by 1/2 or whatever you want to call it. So if you take 1/2 of the perimeter, if you get the semi-perimeter, then that, along with the 3 sides, gets plugged into this area formula down here. So here's your semi-perimeter. And you basically multiply the 4 things together. The semi-perimeter is multiplied by the semi-perimeter minus each of the 3 sides. S minus A, S minus B, S minus C are all multiplied by S, and then you square root, and that gives you the area. So it's kind of a funny looking formula. Certainly hard to think about it, but it just gives you the area based on only the 3 sides. Now, are they going to use this or create it? Good, they have an example using it first. So using the formula, they're giving us 3 sides. So the distance from Los Angeles to Montreal is 2,427 miles. The distance from Montreal to New York is 331 miles. And the distance from Los Angeles to New York is 2,451 miles, not drawn to scale. So they give us these 3 lengths. Those 3 cities form a triangle when you connect the lines that go between them directly. What's the area of the triangular region? So we are trying to find out basically the area inside the triangle here. And we want to do that using just these 3 side lengths that we're given. So first, they're going to come up with the semi-perimeter by adding up those 3 numbers and dividing by 2, and they get this for the semi-perimeter. Then using the formula, they're going to take that number and plug it in along with the 3 side lengths and multiply that junk together and take a square root, and then they get the area. And remember, the area will be the square of the units that the length of the sides was measured in. So in this case, the sides were measured in miles, and so the area will be in square. If the sides of the triangle are measured in feet, then the area will come out to be square feet. And so here you have a nice formula. So if you have side, angle, side of a triangle, we have a formula for area using those 3. And if you have side, 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 this gives us a formula for finding the area based on just those 3 measurements as well.